basically, the idea behind this talk is communication is written in this sort of tagless final way, which is that mine?
I think so.
Okay. Which we try to make this as a selling point of how we could actually develop software in our chain, especially in other modules where I don't have control. But I think that there's like tons of benefits of how we can do it, and I'll just try to sell it here. So there will be some code on slides. After that, I will jump into Emacs because I didn't have time, basically, to finish all the slides. But we should be fine. So I created a little application here that I want to show you guys. So that application, if you run it, it's a very simple application that does very little, but it's complex enough for the demo purposes. Oh, and it doesn't compile. Yay! That came prepared. I know. Oh wait, no, it's actually wrong repo. So we should be fine. Come on, come on. Compile. All right, now run it. Do you guys see it, or you want a font bigger? All right, so the idea here is we have a little REPL here where you have ability to create users and send them over to some server. So the way to create a user, you just provide your first name, last name, and age, and there's a REPL, so you have some. Well, it doesn't work right now, for whatever reason. But you can send those at some point. You provide something that doesn't make sense, and the program will execute with an error, like for example, unparsable line exception. So this is the idea behind the program. So we collect data, we parse that data, we send it over the network. The server receives it, gives it an information back, and then we loop that REPL and continue. So that's the demo, and that's the first approach how we could have implemented. So here are some domain classes that we are using. So there's an error. This is like pretty straightforward. So there's an error type. There's a configuration for our server where it lives, and there's a concept of terminal. This is sort of like our state, because every time we will put something into the REPL, we'll keep history of what we put into it, so that we can have a completion and stuff like that. And also this console thing, it's effectual. It should be closed over task, but for simplicity reasons, I just left it as it is. So that's just a slide about the domain, and also we have our user class. So it takes the first name, last name, creation date, age, and Boolean flag, whether it's active, yes or no. And we have this ability to send that user over protobuf or whatever with this add user message. So that's pretty straightforward. And this is how our REPL could look like. So we could from the state and we could get the terminal. We could read the line from the terminal. Then we could parse that line, having that, it will just give us a first name, last name, and age. Having that, we would collect the current timestamp, create a user with all the arguments that are needed to create a user, send that message, and if we get the result back from the server, we would just print it out, and at the very end, we would update the completer with our line. So the user inserted the line over here, so we update our completer here so that the next time that the REPL is being used, that line is available for completion. So it looks pretty much straightforward, right? No magic. You can run that REPL in forever, and it will work. So if we look at all the like individual functions that are listed here in this for comprehension, they will be straightforward as well to sort of reason about. So we have, and obviously we want to be FP, we want to be as close to purely functional programming as possible for testability and correctness and all that magical unicorn stuff. So now system current time meal is effectful, so we close it over Monex task over here, pretty straightforward method. There's a host and port methods which will give you a host and port from the configuration, and they are closed over reader monad. So that is pretty straightforward as well. There's a method create user. Now this method returns an either type because there's a little logic here, like if you're below 18, we cannot really create a user for you. If you're if you're grown up, and then yeah, we'll create a user for you. So that error message is returned as within the either type. And send message, I didn't have time to implement it, so we emulate protobuf calls here, whatever. But we can imagine that we need this sort of two capabilities here. We need to read configuration, like we want to know the host and port, but we also want to have, we will be doing something effectful, like sending a message over the network. That's why we close that over reader T of task. And yeah, the method probably would be a little bit more complicated, but not that much. The parse line just parse the line, but there might be an error because there might be some issues with that line, so that the return type one more time is closed over either of error or the stuff that we are expecting. And update completer, like the code isn't really that important here. What's more important is the fact that we are using a state monad. So we have a terminal as a state, and we modify it, we do some modification to it, and that's how the update completer method works. It just uses the effect is closed over state monad. So yeah, so now we can use it. Can we? Well, unfortunately we can't, because monads do not compose, right? And now you have to provide this little type here that will accumulate all the effects. So you need to have ability to reason about your state, about your errors, about your configuration, and it's about some code that is effectful that you have to close over a value. So you build this huge effect built on top of the monad transformer. So it's state T of either T of reader T of task. Now, if that seems horrible, let's see how our for comprehension will look like in Scala. And this is it, right? Sorry. Yeah.
Oh, and I was going to point out that like the order that you compose those changes the
Yes, the order that you compose those changes everything. But I don't want to go deep into that. So let's stay here. So that's, yeah, so this is it. And yeah, it's like if, yeah, so much cleaner, right? And if you try, now imagine you try to sell FP to some developer, you try to sell them the idea and you show them this, right? I know what you're thinking. You mean, learning about FP is learning about functional composition and all that stuff and everything else, right? But anyway, in Scala it looks ridiculous. There's an old joke that teaching FP in Scala is 10% teaching FP and 90% apologizing, and that's basically what it is. But my question, so I try to make a point here in this presentation that we can actually handle it a little bit in a Scala, and it makes so the things that we would like to deal with are maintainability, readability, and testability, because the code that we have right now is not maintainable, not readable, and not testable at this point. And we want to also be as fast as possible, because unfortunately the way that the monad transformers are being dealt on the JVMs, they are basically slow. And they are slow for two reasons. Tim pointed me out to a very cool podcast with John Begos, where he goes specifically into details of why that is. But basically in general terms, that there is a problem of building those objects all together just so you can then flat map them or bind them. And there's also problems on how the JVM calls are being made if the underlying type is unknown. So we would like to, our final effect, our final type should be as close to task as possible as we can. But with monad transformers, this is not doable. So here comes the MTL style. So, yeah, that slide should be, yeah, so, but before we go to MTL, I can just show you that actually, even though that code was horrible, the for comprehension, the underlying, like when we actually use it at the end of the world, the main method is pretty straightforward. We create some stuff which is effectful, and then we have our REPL here we call forever, we'll just loop it, and at the end of the day we run it with some initial state and with some configuration, and we call unsafe run sync, which will just run the task for us. So from the main perspective, that's pretty cool. But we would like to deal with the implementation stuff. So let's go back to that method. Actually, So let's go back to that method over here, like create a user. What's the problem with that method? The problem with that method is that we are making a decision up front for people who will call our method. We are saying it's going to be an either type. But then later on, they have to plug it in to our state T of either T of reader T of task, and they are in pain. Wouldn't it be nice if we could, so instead of just returning an either the error or user, we could create a method that we would let the user to decide what the f is going to be. So we would say, create a user, and I'm going to give you an user, but we also would like to manifest that there might be errors in it. But the idea, the general idea behind this encoding, this syntax of this method is that the user makes the decision of what the final type is going to be. But we still need to have, like, we could implement part of it, right? We could make our f applicative. Then if the age is all right, then we create that user and we just call pure, so point on it, and we lifted that into f. So we are fine here. But the problem is, well, what happens if I have actually an error? How can I close an error over that final f that we're supposed to return? With this semantics, we cannot really do that. But there's a type class called Applicative Error, which has this very cool method called rise in error. So it's saying, if you have an instance of this type class for your f, and you have an error, I will give you instance of f of a, of that f, for that error. How? It depends what your f is, right? Because here, that f can be anything. It could be either t, it could be something else. But if we make a constraint that our f is constrained by applicative error, so this error handler here, there's a little type ls here, so error handler is just applicative error of the error. So having this, we now have ability to call method rise error with the error as a e here. So now we can just say, whenever there's an error, raise an error, we provide the error of the type the error, and that's it. As magically we have ability to lift our error into our f. How that's being done, we don't know. It sort of depends, right, of the underlying f. But that's for the user, for the caller to decide. You want create user to return the user value closed over either? Fine, as long as there's an instance for applicative error for either. And there is one, it already exists, right? So this becomes much cleaner. And we could go through every single method within our application. Same applies for reader. So here we are very concrete. We are deciding that you're going to get a configuration, but we are deciding for the user how that information is going to be passed to him. We're saying it's going to be passed through reader. But one more time, we would like to have something different. We would like to say how the configuration stuff will be handled. Well, this should be deleted. Will be handled over some f, but you decide what that f is. And one more time, there is a type class for it. It's unfortunately not included in cats. The Edmund, who was supposed to provide cats MTL project, resigned from type level, leaving the project not really. There's nobody, I think, working on it right now. So, bunch of the stuff. At some point I will jump into the code. You will see a bunch of boilerplate that's only there because I had to recreate things that should be in cats from the day one, but they don't exist. So one of them is actually monad reader. So important thing is this little method ask. It looks like reader, right? Because it has the same capability. It's saying, I will give you an f of s, where s is that configuration thing, as long as you provide me an instance of that monad reader. So now our method can look like this. We will say config reader is monad reader of f, and here we have a nice method that will just give us an instance of this. So now we will do what we did before. We will call asks. That gives us a configuration here, server port. So that difference, the main difference between this method and what we've seen before is that previously we're explicitly calling reader. We're explicitly calling a very concrete type which has this capability of giving us that configuration so we can do with that something with that configuration. Here, for example, take the server and take the host out of it. But with this encoding, we are basically saying we don't care what that f is going to be. It might be a reader, because there is an instance for monad reader that reader gives us, the reader t. But it doesn't have to be. It can be anything else. As long as you provide me an instance of it, I'm fine, and I will give you ability to reason about whatever you want to do. I will just give you that configuration for you. But one more time, we don't really care what that f is going to be when we are writing this function. The user has to decide, and he is in control at this point. Because he's saying, I'm going to use your method with this type, whatever that type is, and we are saying, fine, you can call us with anything that you want, any higher kind of type at this point, as long as it follows those constraints. And yeah, there might be a question like how would we deal with this stuff? So we have current time method, which was doing some effectful computation here, just giving us a current system time. What could we do about that if you would like to close over some f where we don't know what that f is? And there's a nice type class that you could use. It's called capture. It has different names. Different people use different names. I think Cat's effect call it eval or something. Maybe sync. I don't remember. But the idea here is that you can close any effectful computation over some f. And one more time, what that f is, we don't know. It might be a task. That f might be a task, but it might be something different. As long as we provide an instance of it, we're good. So now,
quick question.
Yep.
Am I right that with capture, the by name parameter, the lazy parameter, is really the important part of capturing? In fact, you're not evaluating that.
Oh yeah. So this point over here, right? Like if you call me with something that's effectful, like for example system.currentTimeMills, it will not evaluate. This is by name. This is lazy. This is like Haskell, right? So it will postpone until this is actually being used. So this is like call by name, lazy evaluate parameter. And same thing applies for, and I just want to quickly, I know there's a lot of slides, I'm aware of it, so I want to quickly skip through it. So there's the same principle applies for state. So one more time we have this update completer, which just deals with state. One more time, we don't want to decide by the user it has to be a state monad. We want to say it can be anything, but we will constrain it by yet another type class called monad state. And if you look closely at the methods defined on monad state, they reflect there's like strong correspondence between this and the methods that you actually have on a state monad, because the idea is basically the same principle. I want to deal with state. I want to have ability to reason about my state, which is changing over the evaluation of my calculations. So one more time, we can have this function being implemented, and one more time, we have ability to modify our state, and we're good, but we are not deciding what the f is going to be. So this is the same REPL written in the MTL style. So right now, all those different functions here require different capabilities. So like current time needed capture, or send message needed monad reader, or update completer needed monad state. So when we call all of them together, we need to provide an f that will collect all those capabilities. And that's what we're doing here. We're saying whoever calls REPL needs to provide those capabilities. They need to provide a type that will have all those capabilities in order to REPL to work. Now, the easiest type that you can provide is this. We can still run our software using monad transformer, because that big, huge monad transformer, state t of either t of reader t of task, it contains all the instances that are needed. Either t implements applicative error, state t implements monad state, reader t implements monad reader, and there's an instance that I wrote for task. So now you have this REPL, which is still unaware, completely unaware of what type it's going to be used with, but you're constraining that type with all the capabilities that are needed. And you can run it with our monad transformer. So you might be asking me, okay, so what do we gain here? Do we gain performance? No, because we're still using monad transformers. Do we gain testability? Well, not really, because if I would like to write for example, I want to write a test for this, I want to say, like, for example, this timestamp over here is being used for create user method, and that timestamp becomes an element of the user. That's part of the structure. So that's, for example, I would like to write a test that I would say, like, if the current time is 10, then the 10 will be part of the user that is being created. I cannot still really do that because underneath that current time, it's closed over capture, but it's still calling that underlying system current times mill. So we don't gain testability here, but what we do gain is a little bit of more cleaner code especially when we write those functions, and when we put all those calls together, I would argue it's definitely more readable. But the question would be, can we go further? And yeah, and that's where I have to jump here. So stay with me. So what we could actually do, and this is something called tagless final. So I have two things which are effectful, which are not allowing me to test my REPL. One thing is console, because the console, whatever the class name is, console, sorry, MTL style. The console reader, this guy, is effectful. So like if I try to run it within my test, it will just run typical methods on the console. It's effectful for computation, and also that time thingy is also effectful. So now the question is, what can we do about it? And the idea is here, it's sometimes referred to as tagless final, is that the fact that that capability, for example, printing stuff to a console or reading stuff from a console, we can close it over type class one more time. So now I'm saying this is something that I've created specifically for this project, because monad reader, monad state, those are the type classes that you would normally use, like those are more common, more general. But here, for my specific problem that I have, I need to have a capability of reading stuff and writing stuff to a console, so that I can provide this type class with all the methods that are needed, so read line and print line, and then I could create an instance for it. And this is what I'm doing. This is what I'm doing over here. So let me show you. So I provide a dayline console IO, which take console reader as an argument, and provide instance for console IO type class, so the type class that I created, which will just reuse this stuff. The same applies for time. So I could create a type class which is called time, which only at this point have this one single method, which will give me current time millis closed over some f. I don't really care what that f is. And I can, for example, create a instance of this type class, which will return time closed over task, and we can call it instance system time. So what really changed in our implementation? So the previous program stays pretty much the same. The only thing different is, let me just skip to, yeah, whatever. One second, came up prepared. Fix that. There we go. So you guys see it? The font? Yeah, all right. So the only difference within the program that we've seen before and what we have right now is that REPL is above this method. It stays the same. So it still is, maybe I should just show it to you guys. So that REPL, where are you? Here. So that REPL is still the same. It still is it's completely unaware of what f is, but got two additional constraints. One is console IO, and one is time. So again, we're saying you can call me whatever you want as long as you have instances for those two type classes. And then if we look how that's actually being used, so main method over here, the only difference is that I provide those two instances over here, and now this whole program can run. Now, the question might be, so what did we gain? Well, actually, right now, we gained that testability that we wanted to have. Because if we look at the specification, what I could do is, within my tests, I could create a test, a final effect for my test. So the only difference here is just within tests, it's still state t of either t of either t, but no longer task. It's eval. Eval is like, it's effectively doing the computation at the given moment. So for tests, we are closer to like, so if you run the call, it will immediately evaluate. So and then I could provide instances of console I/O and time which are stops. So let me show you. Actually, I think I have stops. There we go. So for example, just for tests, console I/O can have constant read line. So whenever you call read line, it will always give you that line that you provided as an argument. But whenever you call print line, it will do nothing, but it will store the lines that you tried to print it out to some mutable list at this point. Not mutable, but the list that changes its value by referencing a new list. So then, and the same can go with for time, right? I can create an instance for time, which will just always return that TS that I told it so. So now, when we're writing our tests, the whole description is basically here, but I can reason exactly what the timestamp's going to be, and I can also reason about, like for example, about my console output, that it will have this string and it will have that string. So now, if we look at closely at what that is giving us at this point, is that it pulled all the details to the boundaries of our application. Like if you guys familiar with hexagonal architecture or clean architecture, whatever, this is exactly what it is. How I push stuff to the console is a detail at this given moment. How I read timestamp is a detail. Same would go for sending messages. Like the fact that I'm using gRPC is a detail that I shouldn't be really concerned when I'm writing a business logic. Now, so I don't know, is that a selling point or? Yeah.
I mean, classically, you're just saying separating interface from implementation, right?
Yeah, it's basically what that is.
You could generate an AST of case classes that just have all of the function calls.
Yeah, so I will argue you can write good software in every language and every paradigm. The only question is how much of cognitive power you later on need to sustain the nice level of robustness in it. How much the compiler and the paradigm will help you to not allow crappy code just slipping into your code base, and how much you will have to rely on code review to go through every pull request because maybe somebody will just provide something which is not cool for your design. But yeah, this is basically what it is. It separates that sort of implementation from the interface.
So one of the things that you can do is you can say, well, I'm using reader, but I don't need local, and I don't need this and that.
Yeah.
And so you can say, okay, well, I can actually create a type class that's tighter.
Yes, you can specify a tighter type class that only provides those methods which are needed. Yeah. There still is a little bit of problem, and the problem lives in the matter that if we look how the encodings are within the functions that we use, so all those functions like REPL and all the other functions that we are using becomes not much cleaner, but at the end of the day, we are still using this huge monad transformer. Now the question would be, what could we do about it? And the answer is, well, we could actually flatten that type, because we don't have to we don't have to use reader T to provide an instance of monad reader. We can imagine there will be some place where that configuration is stored. That instance of monad reader will have an reference to that configuration, and whenever you ask for it, you will give it to him. And that's what we're gonna do here. So, and I'm closely to finishing this, so stay with me. I know there's a lot of code. I'm pretty aware of it. So what I did here is you can already see that this type is a little bit tinier. I removed the reader T part. Okay, so you might be saying, well, shouldn't compiler complain that there is no instance for monad reader? Well, it should, but I've also provided, so let me show you. So I've added 2 classes, and this one is actually stolen from remotely. So it's a class called taskgraph, and taskgraph will hold atomic reference. So whenever you do modifications to it, it just allows you to have a single call actually modifying this. And if you look at the signature, it resembles a little bit of a state monad at this point. It has a modify, it has a write, it has a read. So just based on that, we could actually provide instances for monad state and monad reader. Important thing is that when we create an instance of taskgraph, when we create it with some initial value, what we get back is not really taskgraph, it's task over class taskgraph. So we are not getting an access to the underlying thing that is close over atomic reference. We get a recipe of how to evaluate it. And also, every method that modifies it, read, write, modify, whatever those methods which are listed here, that will not do the modification when you call those methods. They just return a recipe for this method to run at the end of the world. Because what we want to do in functional programming, we want to build this huge big function which is called at the end of the day. So there is no, at first when you look at it, you might be thinking, oh, imperative code. But it's not really, because it's still every call is closed over task. It just postpones the effects that it holds. Like, for example, modifying the internal value under atomic reference. Once we have that, we can go to monad reader. Yeah.
So you wrap the task graph in a task, and by nature the task is supposed to be like for the asynchronous computation. Could we do the same thing like we did when we moved from the monad transformer to MTL, that you wrap it in the like arbitrary f that
like
has
capture? Yeah, you could.
Or
yeah, you could, but I'm only using this at the end of the world where I actually want to use task. So I'm not really, I'm specifying the type very, very explicitly that's going to be task, because this is what I want to use in main method, not anywhere else.
But if all your calls in the main method will be synchronous, to run a task, you still need execution context, which would be like unnecessary if all the calls are synchronous. Right? To call unsafe run async, you need an execution context.
That is correct.
Okay.
So that's I promise we're reaching the end of this. So there is an instance for monad reader and we that local don't really like, we really care about this ask method here. But the thing is, we provide an instance for monad reader for task and some arbitrary R, in our case that R will be the config class, as long as you will give us task reference to that instance. So when you instantiate it, you need to provide the value, the configuration closed over that task graph. So now if we go back to our example here, you will see that we no longer, previously, when that was a huge monad transformer stack, we had to run it with configuration. Right now, this configuration, the monad reader, is provided here using that task graph monad reader. So config becomes a task of task graph that's available for us, closed over atomic reference, and we provide this instance closed over that task graph. And we can do the same thing, and I will not go into details right now, but we can do the same thing for reader. For state monad. So we can provide a monad state of task of terminal with the, let me show you this, it's over here, initial state. So initial state will be closed over task graph, and we can provide an instance of monad state with that task graph. Now, the question is one more time, what does it give us? Well, in theory at least, we ended up in having a type which is very, very flattened. It's really close to a T. Like, we still have a monad transformer because we still have either T of task, but we are done with 2 layers of monad transformers. So at least in theory, this should be more performant. Question?
Task includes arrays error, so you could actually throw that one out too.
No, well, not yet, not exactly, because the problem is that the arrays error gives you the f of throwable, and the applicative error requires f of a. So you could cheat, and I was hoping to cheat, but I was hoping I will have like 2 more hours to prepare this presentation. You could cheat a little bit, but this is something that you wouldn't like to use in production. However, that was my selling point for Greg, because I'm really would like to convince him that we should use Scala Z, because within Scala Z8, the final I/O is parameterized by 2 types. One is the A, and the other is the error type. So you can actually write an applicative error for task, and your final effect will be just I/O. But yeah, we could cheat. However, I have benchmarks for you guys, and they are promising. So, well, not in this comment. Yep, give me a second. There we go. All right. So, and this is important. Like, this is the whole beauty that we're gonna get from this tagless final approach. I have a program here written for those. That's not needed. Written for those benchmarks, and program is fairly easy. We're using the functions that we created before. So we're reading host from configuration, and so do we read port. And now, if the host is localhost, we will raise an error host not allowed with our localhost. If the host was something different, then we will just return it as a host, port, and return it as a value server here. And then within terminal state, we will just store into history that server, that value that was provided. This is very straightforward program, right? Does it make sense, this program so far? And check this out. This is written in that tagless final way of writing software. So I'm not saying what those f's gonna be. I'm saying just need to have ability to handle error, it needs to have ability to read configuration, and it needs to have ability to manage state. And then we have 3 different benchmarks. I will tell you in a minute why 3. Maybe I will just show you the first 2 at the beginning. So the first benchmark is using monad transformer stack, and that's the beauty of it, that I can, for both of those 2 benchmarks, I can reuse the same program. And if I'm not happy with performance, then I can actually do something about it. But I'm doing something about it, not trying to find little places within my code. I can reason about it at the boundaries of my program, where the type classes are defined. So my program will be called with, let me just show you those effects. You still see it? So we have here the monad transformer, which is state t, either t, reader t of task, which provides all the capabilities that our program needed, and we can run it with initial state. We can then take value from either. We can run it with configuration, and at the end we'll get task, which we run. And also we have an equivalent program, which is using flatten effect. And flatten effect here on line 63 is just that either t of task, and there are instances for monad reader and for monad state, which are implemented with taskgraph. So the stuff that we've seen before. And I could run it. Just to prove that it works. But I actually have the values over here. So how many of you guys are familiar with GMH output? Okay, so GMH will run benchmark for us. We'll do the warm up for the JVM. We'll do all the things that you would probably break. It will do it for you correctly. And you can see that here, the monad transformer stack, when it was in mode throughput, was able to do 0.367 operations per microsecond, while this exactly same program that was using this flatten type could actually do it 3 times fast. Now, there is one more benchmark here, which is called RWS and either t. I can actually show you guys this. So this is something that Tim pointed out. There's a very weird class which is called index reader writer state t, and you look at it and you may be like, what the hell? And then you read comment and it's just saying, in other words, it's a reader t and writer t and state t. And at this point, okay, so why not to use them all together? Well, as you can see from, so the final benchmark that we have, the last benchmark that we have, is calling that program with this effect. So this effect is very similar to the effect of flatten effect. Okay, let me show you that effect. So that's either t of that indexed reader writer state t. So that is this huge class that collects everything all together. And apparently, this is magnitude as fast as the previous approach that we had, because it sort of accumulates all that stuff from reader and state. There is obviously a scenario that maybe I don't know how to write benchmarks, and maybe I said there's some problems. But this isn't really the issue here. The main issue and the main selling point I'm trying to achieve, well, is that the program, if you look at those benchmarks, the program is exactly the same. We can write programs which are readable, which are testable, and if we have performance issues, we can deal with them globally. It's not that we're going to choose state t and either t, and at some point we will realize, holy crap, this is slow, and now we have to redo all the functions called in our projects. We could do it at the end of the world in the main method. And if let's say that reader-writer state class is slow also, maybe there's other approaches. Like there's atomic queue, right, that we could use. There are a bunch of other ways to approach the performance problems, because there is no like a silver bullet for it, right? But the issue here is that we can do it regardless of how complex our program is. So this is how really quickly, this is how
I think also if you have I think also if you have an optimization pipeline, this bundles it all up into a package that optimization pipeline can act on before you run it.
Yeah.
So there's even more opportunity for fixing problems after you've built the program.
Correct. So this is how communication works right now. The communications, when I joined, it was fully imperative, but I could provide that boundary really clearly between the FP code and the imperative code by closing everything that was imperative into capture. That didn't give me any testability whatsoever, but at the beginning it gave me a very clean line where I want to be and when the rest of the code is. And what I've been doing for the past 2 months was just slowly pushing that boundary, removing the imperative stuff, until I reach a point where we have an ability to test our protocol. Like we can reason about what should happen within Node. If you're connecting to a node that you haven't seen before, the first thing that you need to do is you have to send an encryption handshake message with a public key. And then we stop the communication effect. We provide a communication type instance of communication type class that will remember every call that was being made to it. So then when we call connect method, we can assert a few things. Well, first of all, that there was a request actually on our list of requests, so somebody actually called round trip method, and that it was actually an encryption handshake message, and that message was holding a public key, and that public key is actually what we're hoping it to be. And we can write all the tests for all the protocol that we have without running peer-to-peer network. Well, by just basically putting the details away from our unit tests. And my plan for the next... Yeah.
Like essentially you could build up...
It should be on. I think it's on now. Just took a moment to go green. So for the implementations of for your instances, theoretically, you could also like build up case classes, and you could have an entire AST of all of your effectful code that then you could go and inspect and look at. Right?
Oh yeah, if I like pain, yes.
Well, but it's just like an interesting, like maybe there's some way to capture optimization by like then going through and
oh yeah, I agree.
Applying optimizations to your AST.
Yes, I agree. Like you could for every call you could create a structure,
right.
And then you could reason about the underlying the structure that was finally being built.
Right.
So you can reason which elements of the code were being called first and which order and whatnot.
I mean, it's wacky. It's just to sort of goes to show that there's all sorts of things you can do.
It gives you this flexibility. So I'm trying to sell a few points. The methods will be cleaner to read because if you like the boilerplate, I mean, if you guys are previous Java developers like me, you are pretty familiar with boilerplate, right? But I would reason that maybe this is not the right way to write software. So cleaner methods, maintainable methods, testability, and an ability to reason about the code in different ways, especially in terms of performance and tests. And that's all I had to say. I will just add that I will try to spread through our chain this approach. So be ready for me nagging you in pull requests. This should be MTL. This should be tagless final. Yeah, that's all I have for now. Thank you, guys. There's so all those within COM right now. So we have, well, there we go. All those effects are right now defined within COM because those are COM specific. But as it turns out, right now the metrics API needs to be defined, like it's going to be used in storage. So this effect will go into shared library, and so that will be used because. Just really quickly, the node Scala is the place which puts all that stuff together. There are still things which are imperative, and they are being called imperative, and at some point I hope they will disappear, and they will just be closed over task. But essentially, if we have a thing like runtime could return an effect of F, that would hold the metrics API, which you could use. So that's slowly spreading through the rest of the code. Hopefully, by the end of the Mercury, it will spread like a virus. Yeah. All right. Thank you very much, guys.
Wait, are there no more questions?
Oh yeah. If there's questions, I can. Yeah, so Tim, you were asking what are the performance benefits, right? So we can clearly see that, we can flatten that at the rule. The one thing I want to do is right now, maybe after this session, is that as Kyle said, I can provide a sort of wacky, weirdy applicative error instance just for task. It's doable. It's going to be weird. It will just task, right?
Just write our own task and parametric in the error. Yeah.
Or that, yeah. Or use Scala Z8. And see how that will perform, whether this will perform better, yes or no. And also the question is, do we really have to, for example, close the value like configuration or state close within a task graph? Like if it's going to be used in one place, maybe it's worth also to have it like access in that particular place. But
the config ref you can probably not make atomic because it's just read only.
Yeah, it's just while the state is probably better.
Yeah.
Yeah, and also task graph was stolen from a very old version of remotely. Scala Z8 right now has its own version. Monix has its own version. So I haven't tested it with those implementations. Maybe they are more performant. But one more time, that's the optimization that we can do later on. If there are no questions, I'm done.